Hi, so without further ado, I think we should start the session. I'm Ian Stewart, I'm convening the next session. I'm the research group leader for nuclear theory in the LNS, or in the CTP, which is part of LNS. I've been at MIT for 15 years, so less than my colleagues, 30% of the time of the CTP. And I'd like to introduce David Kaiser as our first speaker. So David is MIT's Gershachen Professor of the History of Science and Program in Science, Technology, and Society, as well as a professor of physics. He started at MIT as an assistant professor in 2000, and amongst other things is well known for his work on the history of physics, including his popular books, as well as his more recent work on cosmology. Today I'll take us back 50 years to look at the CTP in the early days.
Thank you very much. So hopefully the first, there we go, perfect. Okay, so I want to bring us back. I'm going to try to be efficient and bring us back to a mindset of 50 years ago. Some of you will recall this album that we're celebrating, from which I stole my top line title, was released in June of 1967, maybe coincidentally, but in June 1967 was exactly when the contractors began making the space for the CTP. The cosmic coincidences we can explore together later. But I do want to also highlight the Fab Four. So here's Vicky Weisskopf overlooking the work of the first three directors of the CTP, whom you may recognize, Hermann Feshbach, Francis Lowe, and Arthur Kerman. So it seemed fitting to start us off getting really back 50 some odd years ago. So at the time the CTP was founded, Vicky Weisskopf was the department head of physics. You can tell he was department head given the pose here. That's what department heads look like. And he had authorized his colleague Hermann Feshbach to begin making plans, or to follow through on plans, to make this newly proposed Center for Theoretical Physics. What amazes me is actually how relaxed Hermann looks, because he accomplished something truly extraordinary. I would have thought this would break several laws of physics. He was able to work very closely with both the architect and the contracting firm. They started construction on buildings 3 and 4, indeed the similar space in building 6 where we just were having lunch. And it took less than 5 months between when they began the work to when the construction was finished. That's first and last time in the history of academia that a project was done so quickly. And then Hermann became the first director, the inaugural director for the CTP. So I've learned a fair amount about these early days, the ideas for founding the CTP, what was happening right around the opening, from a really lovely thesis I want to point out by a former student of mine, Juanita Becerra. Some of you in the audience might remember Juanita as well. She was an undergraduate student here at MIT. She did a double major in physics and STS and wrote a really lovely senior thesis on Hermann Feshbach's career. She did a lot of very original work in the archives, spoke with people who knew him, and so much of what I will share in this opening part of my own remarks I really learned from Juanita's work. So as I mentioned, Hermann worked very closely with the architect as well as with the contracting firm, and the basic idea was to take portions of the 3rd and 4th floors of Building 6, which is formally known, although no one at MIT calls it that, as the George Eastman Laboratory. So in the space near where we're sitting right now, and to do a kind of judicious rearrangement. So adding some partitions that hadn't been there before, removing some others that had been, to try to create very intentional spaces in which people could interact informally, often around blackboards or around sort of quiet shared spaces. He explained to the MIT provost at the time, Jerome Wiesner, why he thought the architect had actually done a really good job at this. He'd realized this vision. So I'll read a portion of Feshbach's letter, saying the solution to the problem of converting MIT corridors into a desirable living and working space can be considered a model worthy of emulation throughout the Institute. The way in which the center is separated and yet not divorced from the rest of the Institute showed real skill and good taste. It was, after all, right off the so-called infinite corridor, and yet was able to parse or carve out a kind of secluded space for small groups of colleagues to work and talk together. The student newspaper covered the opening, repeating a line actually from the press release at the time, saying the new CTP space featured 2 essentials for scientists in the field: blackboards and quiet. Although it wasn't all that quiet. In its very first year, there were 40 theorists in residence, 19 members of the MIT faculty who now were affiliated in an official way with this new center, and then several visiting professors and indeed postdocs and others. So it wasn't all that quiet, but they did have finally a unified place to sit. And as you can see here, and I think Bullock mentioned a few moments ago, until this new space was reconfigured in Building 6, Those 19 faculty had been dispersed across 12 buildings on campus. That's a very low number density of theorists per building until they were brought together into one common space. To help launch the center, there was a 3-day symposium, and I want to just point out one more example of the genius and miracle work of Scott Morley. Look at the dates of the symposium in 1968 and how well he got us here today, right? We all knew Scott can do amazing things. They held 3 days of meetings in mid to late March '68. They were actually celebrating the opening of 2 centers at MIT, the CTP and also the Center for Advanced Visual Studies, which is also celebrating its 50th anniversary. This year it has a different acronym now, but the same great basic group. At the opening, the provost, Wiesner, made some very quite nice remarks about the similarities in ambitions of these 2 kinds of projects, that both the theorists and the artists are worried about imagination, they're thinking about symmetries, they're concerned about aesthetic significance, so how fitting, he went on to say, that these 2 groups should be, so to speak, born together. In addition to Wiesner, there were 3 days of talks, symposia. There were whole sessions on cutting-edge developments in various areas of physics and astrophysics. Some of the leading keynote speakers included notables in the field, Julian Schwinger, Hans Bethe, T.D. Lee, each of whom had already received the Nobel Prize by that point. MIT alumnus, Murray Gell-Mann, his PhD alumnus, was also speaker. He went on to win the Nobel Prize the following year. And all told, over those 3 days, the newly renovated space welcomed more than 400 visitors, which is even more than we had for lunch. An amazing sort of through flow to help launch this new center. So for the remainder of my remarks, I'm going to take inspiration from this really lovely logo. I'm going to focus most of my time in the past light cone. In fact, not just the past of 2018, but the past light cone of 1968. Unfortunately, after hearing Frank's talk, I realized the job of historians has just gotten at least twice as complicated, because now we have to worry about influences from the future light cone as well. And I didn't have time to update my talk yet, but at least I can say some things about conditions and events and interactions flowing toward this conjunction in 1968. I'll spend most of my time just trying to make sense of this strange activity, this sort of not obvious thing to do called theoretical physics, and even stranger creatures called theoretical physicists. How do we come to a world where that's a job description, where people get paid, some, to work on that as their job? That's a new thing in human history. And then I'll say more briefly, I'll linger on this sort of equal time surface of around 1968, what else is going on in the hallways and neighboring hallways of the CTP. And then I'll close with some reflections, very much picking up with what Wadi just shared with us as well, about the kind of time scales or time constants to think about the elaboration of major lasting ideas in theoretical physics. So there's lots of work that we can point to when we look to the past that we see has obvious continuing relevance, maybe even still inspires us today. We can go back to the 17th century, a period often called the scientific revolution. We can think about work by Galileo or by Newton. And it's important to remember that we might recognize and even make use of that work. They were not doing what we would call physics. They were certainly not called theoretical physicists in their day. There was no such thing. There's no such label. In fact, they spent most of their careers being paid as mathematicians. The big break, when Galileo was hired by the de Medicis and finally got a big raise, is he could call himself a court philosopher. So he got boosted above the level of mathematician. I want to pause on that for Mike Sipser, if he's here. My friends in the School of Humanities, Arts, Social Sciences insist I drive that point home. The philosophers were considered way above the mathematicians once upon a time. So we draw upon the tremendous insights of these people. They did not think they were doing something called theoretical physics. The term did not even exist. Let's fast forward another century, think about the grand traditions in what was often called rational mechanics, the great, mostly French tradition, names again that we'll recognize, Lagrange, Laplace, we get at others like Fourier. Again, not one of them was employed with the title physicist, let alone theoretical physicist. They were again largely called mathematicians. On occasion they were hired as astronomers. We have to come quite a bit closer in time, about 1 century before the founding of the CTP, not 2 or 3 centuries, but about 1 century before the use of the term physicist as a job description even comes into common parlance. And an example I like to share is from James Clerk Maxwell. Just a few years after his great triumphs, which we still put on our t-shirts and coffee mugs, Maxwell's equations, when he brought together all these tremendous insights into electromagnetism, his great promotion was to become the inaugural director of the Cavendish Laboratory. So imagine, Bolek, if we rewarded the best mathematical physicists by giving the keys to all your equipment, right? Or Ray Weiss. This is not how we do things today for everyone's safety. So Maxwell's job was to handle rooms like this and make something useful of them on the heels of having done what we would consider his grand achievements in theory. So the notion and the job description of theoretical physics is pretty new, at least on the timescales that historians will sometimes think about. In fact, many historians have kind of gone over this. The consensus view seems to be that the notion of a job called the theoretical physicist, something approximating what we would recognize today, really dates to the closing decades of the 19th century, so not even a whole century before the founding of the CTP, and really took form based on some of the peculiarities of the German university system. There's a really impressive 2-volume study of this by the historians Krista Jungnickel and Russell McCormack. Together, the books are 800 pages, so I'll summarize in a few quick slides. But their argument I find really fascinating. And it turns on certain things like the fact that back then, German universities, in the German-speaking lands, I should say, there was not yet a country called Germany, but in the German states, most universities had a single full professor, so-called ordinarius professor, in a given field. There would be one professor of philology, one ordinarius, one full professor of physics, one full professor of mathematics and chemistry, and so on. In the physics case, the ordinarius professor actually controlled, and in some sense even owned, the apparatus. So again, Bolek, imagine if you owned all this stuff from the LNS, if it was considered your personal property, and you can trace that through all kinds of records. So the ordinarius was in charge of that, could at his discretion, allow other members of the department to make use of the apparatus. It was really tightly controlled by the single full professor, the ordinarius, who was by definition an experimental physicist. Well, starting in the middle decades of the 19th century and really accelerating after there became a single unified country of Germany after the Prussian-Franco War of 1871, there was a concerted kind of organized effort to do very rapid industrialization within Germany. Again, some of you may know that Germany within sort of 2 or 3 decades started exceeding the industrial output by anything you could choose to count of the other major European powers. Things like these enormous steel works, the railroads, and all that. So now that there was a single unified Ministry of Education that could start placing faculty at all the universities within the whole country, they realized to support things like this, they're going to need a lot more secondary school teachers to teach things like physics and math, especially physics. So they need to have a very rapid reform of the secondary school education system, and they need a lot more physics teachers. Well, once you decide you need a lot more physics teachers, what do you do at the universities? You start hiring all kinds of junior faculty. So these younger faculty were called extraordinarius professors, not because they were considered extraordinary, but because they were considered extra, because that doesn't change. A huge hiring binge of these lower, roughly speaking, kind of assistant professor kind of faculty to teach very rapidly expanding classrooms of students, in part, or at least justified, by this enormous coherent industrial effort in this newly unified country. So what happens is now you have tons and tons of extraordinarius faculty, most of whom dream of one day becoming a real physicist, meaning an experimentalist, becoming the ordinarius at some university, getting the keys to the cabinet with all the apparatus. But in the meantime, they're stuck. And they're forced to do theory because they're not senior enough to do experiment. So you do this for a generation or two. You build up a huge cadre of some exceptionally skilled people who have grown up only pushing pencil and paper around because they have not yet gotten their big call to become an ordinarius professor. So their work looks more like this than like Röntgen's laboratory. So only after this goes on for a decade and a half or 2 decades do you start realizing, do people at the time realize there's now an activity, a coherent activity we can point to. These people do something, they do something called theoretical physics, and you start only in the closing decades of the 19th century getting ordinarius professorships in theoretical physics. One of the very first was Kirchhoff, Gustav Kirchhoff, whose name we still know, of course, when he was elevated to ordinarius professor of theoretical physics in Berlin in 1874. That was very early for this. It was actually Planck who took over that chair in 1889, and over the 1880s and 90s, this becomes more and more the pattern rather than the exception. So the leading journals like the Annalen de Physik begin hiring subsidiary editors like Max Planck to handle the theoretical submissions, because there's so many now papers in this sort of self-identified specialty But it's all an accident. It was an unintended outgrowth of rapid industrialization. I think that's I'm going to sit with that for a minute. Again, I was trying to run a thought experiment, Frank. If there's really time reversal, symmetric, if we got tons of industrialists today to give us money to train more theorists, would they gain or lose money? I'm not sure which way it would work. Would their fortunes rise or fall? I'm not sure. Anyway, it's a remarkable kind of accident of history that in most of the German sphere, this thing called theoretical physics kind of coalesced, not quite a century before our own CTP. So that's the story largely in Western Europe. What about here in the US? An example, again, I often think about, the very first dissertation in the US on quantum theory was completed by Edwin Kemble at Harvard in 1918, so pre-quantum mechanics. This was kind of Bohr atom, Sommerfeld type stuff. And yet Harvard would not let him graduate until he had done a few experiments. One could not get a PhD as, so to speak, a theoretical physicist. Moreover, and what became a very common pattern, Kemble and indeed many of the other leading figures from that generation who completed their PhDs often in the US in theoretical physics had to take these fellowships and travel mostly again to centers in Western Europe for postdocs. They could not complete their training as theorists in the United States. And that was true of Oppenheimer, of John Wheeler, of John Slater, who of course came back and really built MIT's Department of Physics, Philip Morris, another great member of our department for many years, and many, many, many others. The leading ones to complete their training had to go to the centers like Göttingen, Munich, Copenhagen, and Cambridge and come back. Philip Morris writes about this very nicely in his own memoirs. Some of you might know. A few of the members of that generation came back and became especially gung-ho, especially prolific mentors and institution builders. Famously, Robert Oppenheimer, he was hired at 2 universities the same year. We don't let you do that anymore. So in 1929, he became a professor at Berkeley and at Caltech. And this was before interstate highways. It was a long drive between them. Every 6 months, he and his grad students would caravan down the coastal highway or the coastal road and back. Meanwhile, in 1930, MIT President Carl Compton hired John Slater, who had recently returned from Copenhagen, to basically build MIT's physics department, to rebuild it, to build a department focused on basic research on the pursuit of fundamental knowledge. And Slater was given remarkable sway and resources to build this new type of place at MIT. So that was underway by the late 1920s, early 1930s. And of course, then there was an enormous amplification of those efforts, an undeniable importance with this influx of talent from many, many people fleeing European fascism by the middle to late 1930s. So Einstein, for this story, becomes sort of not very important. He went to the Institute for Advanced Study, worked with very few students, and was not at a major pedagogical center. But these other names I'm sure will be familiar. Of course, eventually we got people like Vicky Weisskopf, Hans Bethe settled at Cornell, and so on. Felix Bloch was the first professor of theoretical physics at Stanford in the mid-1930s, and so on. So you play that story forward in time. By the late 1930s into the early 1950s, it was now possible for the leading experts in the United States who've been trained in the United States in theoretical physics to complete their training in the US and not be required to do that kind of grand tour to Western Europe. So Schwinger, Feynman, or indeed Gell-Mann, who finished his PhD here in 1951 under Weisskopf's direction. So by this point, we have a recognizable role, a job description called the theoretical physicist, even in the United States. Considerably later than in parts of Western Europe, but by, say, the 1940s or 50s, certainly. There still was not a pattern of having sort of dedicated spaces, having physical places for such people to interact together. This is a not complete list, but I think it gives the kind of gist, the rhythms, for the founding of physical spaces, institutes or centers, explicitly for theoretical physics. And I want to point out the few that were in the United States up to and including the founding for MIT's. The Institute for Advanced Study is a sort of unusual case. It's not affiliated with a university, doesn't grant degrees and so on. We can talk more about that, of course. It really got heavily into the theory training game when Oppenheimer became the director in 1947, mostly focused on postdocs. Stony Brook founded its Institute for Theoretical Physics, now the Yang Institute, in 1965, and surely that had something to do with their very close proximity to Brookhaven National Laboratory, and then MIT in '68. The point being that at least in the US context, there was not a strong tradition of doing these physical spaces to get people to interact together. MIT was on the early end of that trend, and of course now it's much more common. So I want to focus now on the second main point of my talk, which is that this is kind of a miraculous timing. This was kind of early in the US context to build a center, and if it had been 1 to 2 years later, we might not be sitting here today. We'd be on Earth. We wouldn't have a CTP to celebrate. The founding of the CTP was sort of the last great hurrah before the wheels fell off the bus, budgetarily, in terms of science policy in the United States. Here's the MIT budget in constant dollars. It's, the CTP is being built in 67, 68's the budget high for the university, and it just keeps falling. I didn't bother plotting, we just reached the floor. The bottom falls out, starting after a peak of 1968. 1/3 of the appropriations in 1967 went to creating the CTP space. So let's go ask Marty for 1/3 of his budget this year. That same year when the CTP opened, MIT professor and cyclotron expert Stanley Livingston wrote that the high energy frontier has become the financial support frontier for experiment, indeed for basic science more broadly. Another just way to capture this, I'll go quickly. This plot shows the number of PhDs in physics granted in the United States by all institutions. And we see physics, it turns out, grew twice as quickly. The time constant here, the doubling time, is twice as fast as all other fields combined. It races out of World War II, races again among the fastest growing after the launch of Sputnik, and it falls faster than any other field, starting around 1971, 70-71. And again, a huge confluence of factors on and off campus. You can see this reflected in these horribly depressing numbers for students, young PhDs, looking for positions across all 3 domains: academic, government laboratories, and industrial laboratories. Things were pretty good in 63. Things were really, really anti-good by 1971. If that shape of that curve looks familiar, it's because it really was a speculative bubble. This is like, tech stocks that had burst. And again, I'd be happy to say more about that later on. So this was a very unsettling time when the doors to the CTP opened. This was not sort of business as usual in the scientific community or indeed at MIT more broadly. And it's interesting to think back, some of the earliest discussions filling the hallways at the CTP included things that spilled well beyond the domain of theoretical physics. So in the fall of 68, some of you may know, there was an Army private who went AWOL and was given sanctuary space in this MIT Student Center. And you can see there's a photo, it's hard to make out. This is tons and tons of MIT students sheltering, protecting this one Army private during the escalation of fighting in the Vietnam War. And that really galvanized discussions on campus, so that soon after that, there was a so-called March 4th movement, which was advised by several grad students who were in the CTP as well as in other departments. Visiting professor Kurt Gottfried, who was in the CTP, was one of their informal advisors, and soon Hermann Feschbach was as well. The discussions continued getting heated up throughout that summer and autumn, thank you, of 1969 about the military role on campus and so on. And again, the point is that members of the CTP were right in the middle of this. About almost half, maybe about 40% of the CTP faculty were signing letters calling for the divestment of, or the diversification of funding for the basic sciences away from the Pentagon and so on. People like Herman and Francis Lowe went on to found the Union of Concerned Scientists out of this, and so on. So I'm going to pause now, or my last point I'm going to go through rather quickly. It's very much like what Waddy was saying. It's sort of amazing to me to think back 50 to 60 years ago. Many of the ideas, not all, but many ideas that you can still hear kind of percolating around the beautiful space in the CTP these days were being introduced, were first being put out there in the world just on the run-up to when the CTP was founded, so 50 to 60 years ago. So here again, we've heard many times, Jeffrey Goldstone publishing this is from his paper, his beautiful double well potential, we can see. And yet we know that a lot of this work took many, many years to achieve anything like a kind of recognition of its relevance. Not just many years to understand the full theoretical import. Of course, that makes sense. But just for this work to be seen as relevant at all, to get anyone else to pay attention. Here's another example. It was mentioned Steven Weinberg was a visiting professor here in 1967. His paper, for which he won the Nobel Prize, was submitted from the LNS. But what some of you may know is that this work got 0 citations, including self-citations, for several years, because this was seen as still not relevant to the world. In Sidney Coleman's famous recollection, that this work was deemed important when other people, de Hooft and Veltman in this case, showed that these very strange-looking gauge theories were normalizable. And as Sidney wrote, it was de Hooft whose paper revealed that Weinberg and Salam's frog was actually an enchanted prince. And you see citations begin to reflect that. Likewise, you can go through just very briefly other examples. Quarks, introduced by Gell-Mann and independently by Zweig. I can't show you Zweig's published paper because, of course, his paper was rejected and never published. So you can still download his preprint from the CERN server. It was several years later till there was even anything like the coalescence of empirical evidence for this idea, but even that was slow in coming thanks to some MIT folks that we know. And even years after that, Gell-Mann himself was saying that still doesn't mean quarks are real. He was maybe appropriately cagey on, again, a timescale of about a decade or more. Bell's inequality, something I've written a fair bit about. In this case, it was not 1 decade, but closer to 2 or maybe even 3 decades before any sizable fraction of the physics community considered this even real physics, let alone of interest to what they wanted to do. The CMB, likewise, follow-up papers by Jim Peebles, which were giving what we now consider literally the textbook explanation for CMB physics. His paper was rejected not once, but twice by the Physical Review. So some things don't change. Likewise, another nice example, very young Veneziano was here at the CTP just as it was founded. He had just submitted his first paper in what came to be called these dual resonance models, and the earlier annual reports of the CTP make a lot of his continuing work on trying to understand strongly interacting physics with this new approach. Of course, it was many years later till people began to see new things in his own equations, and many years after that before this was seen as a coherent piece of something like superstring theory. So the upshot of those very rapid examples, forgive me for the pace, is to underscore something Waddy said as well, that the time constant for these ideas, not to even be fully understood, but just to be seen as of interest to the community, is of 1 to sometimes 3 decades, not 1 to 3 months or years, despite our archive citation counts. And also, these many-body interactions are critical. Often it was the work of many other colleagues weighing in and working out these ideas, not only the single author whose work we continue to cite. And so this seems to me an important thing to focus on, that we need institutions dedicated to fostering collaboration. These many-body interactions really, really are important. And as many folks had just said before, we need some way to keep a focus on the long view, to think in terms of decades, if not centuries, rather than months or semesters. Thank you very much. Oh, right. Okay. I was already running off. No questions.
Okay, I'll ask a question.
Lisa. Yeah.
So I actually went to the Galileo Museum, and I was kind of amused because they talked a lot about, well, many things, but Galileo's role in, I guess it's known about religion and the connection to that, but also the connection to war, actually.
Yes.
He was financed by the defense.
Right.
So is he still just called a philosopher and mathematician, even though he was doing this applied?
No, in fact, again, I don't know if Mike is here, but I'll make some enemies now. He was only working for defense projects when he was a mathematician. I will make no further comment on that. He was a mathematician supported by the Venetian Senate, and his job was to help with practical things, including defense-related things. And he got this promotion to the de Medicis when he moved to Florence, when he could leave that behind and entertain at dinner, which is what philosophers do. So his shift was literally to leave mathematics and practical applied things and reach for the heavens and get in trouble with the Pope, because he reached too far. So, more to be said, but that's the short version. Yeah, please.
I'm just curious, when you talk about these many-body interactions, I've
Yes.
heard that like firms like Google are actually trying to make a study of what makes groups interact together well,
Right.
what makes them all productive. Do you have any thoughts to share on that when it comes to scientists?
Yeah, no, it's a good question. I don't have. I'm sure any thoughts I would share would be, we'd all have our own impressions, is I guess what I wanted to say. I mean, I often joke that what you need is, a good espresso maker, right? And those beautifully shared blackboards and comfy chairs. Obviously, it needs more than that. But there are, as you know, sort of formal studies in behavioral psychology and many other fields. I'm certainly not expert enough to know what the strength of those conclusions. And in my own experience, it is some combination, some messy alchemy of kind of free time, good colleagues, and the kind of space, literally a space, but also a kind of mental space where there's time to kind of sit with ideas and with a group of trusted students and colleagues. And I don't know if we need very strong, very highly structured psychology experiments beyond that, right, to focus on. But again, others I'm sure will have other good insights on that as well.
Yeah, we'll take last question.
Salva.
I was recently reading Fermi's biography called The Pop of Physics.
Yes.
And they make the point that Fermi has been one of the best and maybe the last physicists to do both experiment and theory with high level of success. Is the fracture irreversible?
Right. Maybe this goes to something that Bullock was referring to as well. I mean, I don't know. Again, I think there are people with a more grounded view of kind of what it takes to reform large-scale institutions that train many tens of, if not hundreds of thousands of people at a time. You have to think about the throughput problem for higher education, right? And we can talk about tinkering at the scale of a CTP, but trying to change how we train the next generation of fill in the blank. That, there's just that's a highly constrained problem. So thinking about making, I mean, look at MIT, many in the room are veterans of these fights over the so-called GIRs for the undergraduates. What must every MIT undergraduate take? And that is still a topic that will get certain people who are otherwise friendly shouting and red in the face at each other, right? So just bringing out an undergraduate curriculum for like 1/2 or 1/4 of their time is really tricky. There were blue ribbon panels that spent years on this, including, I'm sure, Krishna's own experience. So it's just to say that trying to figure out a large-scale transition, like let's make all theorists really good at experiment and vice versa, that is beyond my own imagination at this point. I'll pause there.
So now we have the third video of the day. And although David didn't know it, he was actually setting this video up very well with his last remarks, because there's a sense in which this is about new ways of thinking about throughput for higher education. David, I don't think he even knew what the video was that was coming, but he set it up very well. So here we go.
I've been a faculty member in the Center for Theoretical Physics for almost half of its 50 years. When I was offered the opportunity to become MIT's new Dean for Digital Learning, a big part of how I thought about the role came from my having watched the remarkable things that my two CTP colleagues, Ian and Barton, have been doing with digital learning over the last few years.
Effective field theory is an important advanced topic for graduate students that is often not taught in a regular course curriculum. In effective field theory, we build quantum field theory that is specially designed to study physics at a particular distance scale while systematically retaining information that is needed for higher precision. My goal in designing the online course 8.E of TX was to take a unique special topics course taught at MIT and make it available to researchers and graduate students from around the world. Since the MIT course is not offered every year, the online version also provides a resource for our graduate students to learn the material. In this way, the online EFT course serves as a repository of information about effective field theory that can aid people's research in high-energy physics, nuclear physics, and other disciplines.
I've always felt it's a privilege to be able to teach quantum mechanics to young, enthusiastic students. We at MIT are a little different. We give 3 undergraduate courses in quantum mechanics. This gives our juniors and seniors a very strong preparation that allows them to do undergraduate research very effectively. Our online efforts aim to make the teaching of quantum mechanics better at MIT, and we also want to share what we learn with the whole wide world. The technology is amazing. We can teach these courses without any compromise. The online courses are as difficult and as challenging as the MIT courses we teach. This online grader is quite amazing. It allows you to check for complicated formulas and even graphs of functions. We don't need anymore to have multiple choice questions. The problems are sophisticated and address all kinds of important issues. So it's official now. Our online course 8051 has become a permanent part of the MIT curriculum. We're very proud about that.
Barton and Ian are 2 among the growing number of MIT faculty who are using these new tools to transform how we teach our students on campus and how we reach learners around the globe. On campus, our MIT students love the combination of, first of all, watching Barton and Ian's video segments wherever they want, whenever they want. Sometimes they like to make the professors go a little faster. Sometimes they need to see something twice or 3 times, they use the rewind button. Second of all, the online problems, which give them instant feedback, give them an instant indication of whether they're on the right track or not. And third of all, after doing the online work, coming to class with the opportunity to ask questions, to discuss, to engage in a classroom whose dynamics have been transformed, made much more interactive by the fact that the students have done the online work first. And how cool is it that Barton and Ian are at the same time giving learners around the world a look at how they teach quantum mechanics and field theory, putting their stamp on the next generation, and defining how quantum mechanics and effective field theory are taught and in fact understood far beyond the CTP.